Hello everyone, and welcome to Chapter 2. Chapter 2 is going to deal mainly with graphing and equations. So we're going to start, of course, with something that has to do with none of that, at least none of that in name. Sections 2.1 and 2.2 have to do with relations, functions, and direct variation. So to get us in the mood of these topics, get us in that mindset, we have to start thinking. If we had a function rule like y is equal to 5x, how would we come up with three ordered pairs that are solutions to this equation? What does it mean by an ordered pair? It means we have to have an x and a y value that would make this true. For example, if x was 1, what would y be? Well, y would be 5 times 1, or 5. Now quickly, think of another 2, write them down. Could be something like 2 and 10. Could be -1, -5. Could be even something like 0, 0. Because what happens when we put 0 in? 5 times 0 is 0. Now we're going to get in with our first definition of the day, a relation. And what is a relation? Well, a relation is a special sort of kinship that you have with somebody, usually a boyfriend or a girlfriend, but not always. But in mathematical terms, what a relation is it's a set of inputs and outputs. Now this is a little confusing, so the ways we represent them might help you understand that. We can represent relations with ordered pairs. For example, we might have a relation that says we have the point 1, 2 in it, or if we put in 1, we output 2. It could have 2, 3, could have 3, 7, and 2, 6. So what this is saying is that for each one of these, this value is your input, and this is what outputs for it. Another way we can show this is mapping diagrams. So this is where we take all our x's and all our y's. We say, what x's do we have? Well, we have 1, 2, and 3. And what outputs do we have? We have 2, 3, 7, and 6. Then with a mapping diagram, we say, which one of these x's goes to which y? We say 1 goes to 2, 2 goes to 3, 3 goes to 7, and 2 also goes to 6. Another way we've done this before is a table of values, where we say we're going to take all of our x's and we're going to take all of our y's, and like ordered pairs, we're just going to put them in like this. So we say 1 is our input, 2 is our output, 2, 3 is our output, 3 is in, 7 is out, 2 is in, 6 is out. And finally, we can also graph these. So we can make a little graph, go all the way out to where we need. 1, 2, 3, 4, 5, 6, 7. And we say, okay, for each of these, the horizontals are x, the vertical is our y. The first point is x is 1, y is 2. Next one is x is 2, y is 3. And we have 3 and 7, but we also have 2 and 6. So these are all different ways we can represent groups where we have one input and that corresponds to an output. Now typically, we have a couple of definitions before we get to the typically. One of the things we look at in relations are domains, and the domains are all input values. Or the easier way to think about this is all of our x values. So for this, our inputs would be 1, 2, 3, and then we already have 2, so it would just be 1, 2, and 3. Domain is our inputs. Range is the same, but for y. So range is all of the output values. for the y values. So for this, if we're looking, what are our outputs? It's 2, 3, 7, and 6. So that would be our range. And then finally, we have a function. This is a special type of relation that we tend to look at. What a function is a function is a relation where each input, each x value, has only one output. So each x only has one y that it goes to. Why do we care about functions? We'll show you how we get this in a little bit. Well, why do we care about functions? Well, let's say we're trying to buy ice cream, and we go to one store. The first store, we know anytime we buy 2 ice creams, it'll be $4. Anytime we buy 3 ice creams, it'll be $6. But for the other store, we'll say we go to a second store because the first one was not available. First time we went in, we bought 2 ice creams and it was $6. And then we bought 3 ice creams and it was $4. And then we bought 2 ice creams again, but it was $12. Now, if I'm having a bad day and I just want my ice cream so that I can eat and wallow in my ice cream, am I going to want to go to the first store or the second store? Well, with this one, I know what I'll be getting for my money. If I have just $4 to spend, I'll know I'll get 2 pints of ice cream. However, with this store, I might get 3 pints, maybe I'll get 2 pints, we just don't know. And this is why we care about functions. Functions are reliable. They tell us that anytime we get an input, we will always have the same output. So, how do we check if it's a function given points? So if we have a couple points like 1, 2, 2, 3, 3, 5, and 2, 6. What we need to do is we need to look for x values that are repeated that go to different y values. So we have 2 in here twice, and it goes to 2 different y values. The way I find simplest to do this is to make a mapping diagram. So look at all of your x's and all of your y's. And then if we have 2 arrows coming from one value, we know that this is not a function, because that means 2 as an input could go to 3 as an output, or 2 could go to 6. So that would make this not a function. With graphing, we get something similar. With graphing, how do we check whether one x value has only one y value? Well, let's draw an example of something that might be a function. A line. So we know that if we go to this x value, we only go to this y value. But what about if we had something that was not? If we look at this x value, we could be going either up to this y value, or we could be going down to this y value. So how do we check with graphs? All we do is we take a vertical line and we slice it through. Any time that this slices through more than once, that is not a function. So we call this the vertical line test. Okay, now we're going to take all of this and apply it to a couple problems for forcing you to do them. So we're going to look, are these functions and what are their domains and ranges? So for this, is this a function? Well, we're looking, do each of the x's only go to one y? So 2 goes to 5, 3 goes to 4, 1 goes to 1, 2 goes to 7. Hold on, 2 goes to 7, but 2 also goes to 5. So, no, this is not a function. However, what's its domain? What are all the input values? Well, the inputs are 2, 3, 1, and 2. So we're going to use a fancy set of brackets here. This is how we notate sets in math. And we say, what numbers are our x values? What numbers are the inputs? And so this is, we have 2, we have 3, and we have 1. What's our range? What are the y values we get? Well, we're going to put this in a fancy squiggle bracket again. What are the y values? We have 5, we have 4, we have 1, and we have 7. So it's not a function. This is its domain, and this is its range. What about for this one? Is it a function? How do we check? We do a vertical line test. We see that there are 2 points on this vertical line, so the answer is no. This is not a function. This one's a little trickier. What's its domain? What are the x values that it takes on? Well, if we're looking, it looks like our x values start at -2, and they go all the way to 6. So if you remember this from algebra, if not, we'll go over it a little bit later. This means that we're including -2, and we're going all the way up to 6, which is included. We put square brackets for included, and we circle if it's not included. So we'll get into that a little bit more with domain and range. For our range, what are the y values? Well, our y values go all the way down to whatever this is, which looks like 1, 2, 3. So this is -4. Now -4 is touched. It actually is part of the range. So we're going to use a square bracket for this. What about on the top? We go all the way up to 2, meaning that we have a square bracket on this. Again, if those were not included, we would use circles or parentheses to mark this. Hopefully this notation is familiar to you all still. All right, we're going to skip 3, and we're just going to take a quick look at 4 for its domain and range. For this, if we look, we have 1 point that goes through 3 times. Doesn't matter that we have one that just goes through here once. All it matters is that at 1 point, we hit this twice. So this is not a function. What's its domain? What are the x values it takes on? Well, it keeps going all the way out this way. It keeps going all the way out this way. So what's the smallest value it takes on? Well, if it keeps going this way, it'll keep going to -infinity. And with infinity, we're going to use that circular bracket for technical reasons, but infinity isn't really a number, so we can't ever reach that. What about the largest number? If it continues going this way, it's just going to keep shooting out until we get to positive infinity. Okay, what about our range? Well, our range, if we go this way, it's going to keep going down. So what's the smallest number we'll get? It's -infinity. What's the largest number we'll get? This keeps going up, so it'll be positive infinity. Right. Now we have a couple of problems for you to practice. Go ahead and look at these, figure out whether they're functions or not, and figure out their domains and ranges. So for this first one, is it a function? So we have 3, -2, 1, and 0. We don't see any repeating x values. So yes, this is a function. What's its domain? It's all the x values, making this 3, -2, 1, and 0. Doesn't matter what order these are in. You can put them from largest, smallest to largest, any order you want. What's its range? What are the y values we get? Well, we get 7, 5, 7, 2. Now notice we have 2 7s in here, but that's okay. These are outputs, right? We're allowed to have 1 or 2 outputs that are the same, right? It could be that $2 will get me 1 bag of chips, but at a discount, $2 could also get me 3 bags of chips. It's okay to do that. We just don't want 1 bag of chips costing $3 or $12. What about B? For B, we're looking, we see 2, 3, 4, 2. Oh no! We're looking, we see 2 to 6 and 2 to -6. So this is not a function. Now our domain is going to be the x values, so it's going to be 2, 3, 4, and our range is going to be 6, 5, 1, negative 6. What about for C? For C, we do the vertical line test all over, and we see that it only ever crosses once. So, yes, this is a function. What's its domain? Well, what x values does it take? If it keeps going out this way, and it keeps going out that way, the smallest x value it will have is negative infinity. The largest x value it'll have is positive infinity. What about its range? What y values will it take on? What's the smallest y value? Well, it doesn't go all the way down now. It only goes to this point, and that point is negative 4. Now, is negative 4 included? If we're looking at this, it looks like it does touch negative 4, so this should actually be a square bracket. What's the largest value it takes? Well, if it keeps going on, it'll go up and up until it hits positive infinity. So this is determining whether they're functions and figuring out their domain, which is the values they take on, and the range, or the y values it takes on. Now, because functions are so important to math, we actually have special notation for them. When a function is written in function notation, we replace the y with an f of x, or of our input. And this just tells us that we have a function. So for example, y is equal to 3x becomes f of x is equal to 3x. So for putting these in, what would this one be? Well, our input, our variable is x. So this becomes f of x is equal to 5x plus 1. What would 2 become? 2, our variable, our input is still x, meaning that this is still f of x, and it's equal to x squared. What about this one? Our input variable, we have to be careful here, is not m. That looks to be our output, right? If we were to rewrite this, we could say that m is y. It's equal to 6, and b would be the one that we're relying on. So we're going to replace m with f, and it doesn't have to be f, it can be g or h, doesn't really matter, but this will be f of b, because b is our input variable. It's equal to 6b plus 1. Using that same knowledge, what would 4 be? So 4 would be f, and our input is c. So f of c is equal to negative 2c. This could also be something like g of c is equal to negative 2c. This letter out in front doesn't matter. We just need to make sure we have something in parentheses. Now, why is this useful? Well, if we get something like this, and we know it's a function, we can just replace whatever's inside with the value we want to substitute for x. So if we get something like f of x is equal to 3x plus 2, we say f of 5, and what this tells us is that x is equal to 5. So now all we have to do is we say, anywhere there's an x, we'll replace it with a 5. So this becomes 15 plus 2, or 17. All right, now you guys do this one, we'll do this one together, and then you'll do that one. So what do we do with this? We substitute in a negative 2 anywhere there's an x. This becomes negative 3 times negative 2 minus 4. Negative times a negative. Remember our triangle. We have negative, negative, positive. So a negative times a negative gives us a positive, making this negative 3 times negative 2, giving us 6 minus 4, or f of minus 2 is equal to positive 2, not negative 2. All right, for this one, we substitute the 3 in. So this becomes f of 3, and it becomes negative. Remember, the negative is outside. If we wanted the negative included, we would have parentheses around. So this would be negative x squared. But when we see the negative just hanging out, it means we're looking at parentheses just around the x. So this is negative parentheses 3 squared, or negative 9. Then for this one, we're going through this, we're going to put in a -2, meaning that this becomes 3. What value are we squaring? Well, we're squaring -2. So we said the negative stays out in this one, but it's part of this now, right? It's part of what's in the parentheses. So it goes along for the ride. And we get 2 times -2. What does this give us? Well, this gives us 3. -2 times -2 is 4, plus 2 times -2 is -4. This gives us 12 minus 4, or 8. Great, now we're going to move on to our last topic, which is direct variation. So my question is, why is it easier to determine the equation for this table than it is for this? And if we're looking at these from a table, what are we doing? We're looking at how much it's increasing, or we're looking at how much it's changing. For this, we see that each of our outputs is just double our inputs. So each of our outputs is just double our inputs. But with this one, we can't say that because all of a sudden we have this 3 here. And so we're going, oh, so 2, I don't know what's happening here. Right, so whatever this will be, we'll have some relation to our variable, but we'll also have a 3. We're not going to figure out what this is, but this 3 is throwing us off. So we made a special name for times when we don't have something throwing us off. That's called direct variation. So this is when y varies directly with x, and it takes the form y is equal to k times x. Our constant of variation is k, we give it a special name, and k is just going to be equal to y divided by x. So now we're looking to determine whether these vary if y varies directly with x. If so, we're going to find the constant of variation. So for this one, we're looking, what's 2 divided by 1? So is k for this first one is going to be 2 over 1, or 2. For this next one, y divided by x is going to be 6 over 3, or 2. And for this last one, it's 4 over 8. Oops, flip that. It is 8 over 4, which is also 2. So each of these are the same, meaning that our constant is the same. So this is constant variation, and it takes the form y is equal to 2x. What about this one? For this, we'd say k is equal to 4, k is equal to 8 over 2, which is 4, and k is equal to 11 over 3. This is not 4, meaning that this is not a constant of variation. What about this? Well, for this one, we need to get it into y is equal to k times x form. So we're going to need to divide by 3. When we divide by 3, we get y is equal to 7 over 3x. Does this look like this form? It does. So this is direct variation. And what is k? Well, y is equal to k times x. So k is equal to 7 over 3. Okay. What about this one? We need to get y by itself, so we're going to divide everything by 7. This becomes y is equal to 14 over 7x plus 7 over 7. Or this becomes 2x plus 1. Does this look like that form? It does not. We have the little annoying bit on the outside. So this is not direct variation. Okay, finally, one last one. We're saying this time we know y varies directly with x. When y is equal to 9, x is equal to 15. Then we're trying to figure out what y is equal to when x is 21. So you might go, oh no, I have no clue where to start with this one. Let's start by writing down what we know about direct variation. Direct variation, if we look back, it should be y is equal to kx, and k should be y divided by x. So we know y is equal to kx, and we know k is equal to y divided by x. Does that help us out at all? Well, do we have an x and a y that we could use to figure out k? We do. We have 9 and negative 15. So we can use those to say, what's k going to be? Well, it's going to be 9 divided by negative 15. Or if we simplify that down, this will be negative 3 over 5. So even though we didn't know where to start, we just wrote down what we knew and saw whether we could use anything in the problem to answer or to help us clear anything out. So now that we know k, we say, hey, we know what the direct variation is. So y is equal to negative 3 over 5x. So now it's asking us, what is y when x is 21? So what are we going to do? All we're going to do is substitute 21 in for x. That gives us y is equal to negative 3 over 5 times 21, which does not look like it's going to be a pleasant fraction. Let's just throw this into a calculator. Negative 21 times 3 gives us, this is going to be negative 63 over 5. So the main concept with direct variation, y changes with x. This also means that when x is 0, when our input is 0, y will also equal 0. All right, that's it for this lesson. Go ahead and get started with the homework.